Okay, so I think I'll kick us off here. Uh, welcome everyone to
Okay.
yep. Welcome to the first keynote of our POPL virtual workshop. Uh, I'm going to introduce the speaker in a way that starts out sounding sort of like what you'd expect to hear at POPL, and then there's going to be a twist. So Łukasz Kaiser, whose first name I've just learned how to pronounce properly, got his PhD at RWTH Aachen, working in logic and automata theory, and he got a permanent research position at CNRS in France, working in logic, games, and AI. He's worked on, for instance, applying SAT solvers to program synthesis. And then, so this all sounds like a normal kind of POPL talk at this point. But then he headed off in kind of a different direction, joining Google Brain and contributing to machine learning tools, for instance, as part of the TensorFlow effort. And he's recently joined OpenAI, the organization behind the Codex project that he'll be telling us about. I'm assuming everyone's seen some of their cool demo videos online. I think this is one of the projects that people are talking about the most in the developer world. And we're very glad to have Łukasz here to tell us about the project and give us a chance to drive an interactive demo that will come after the slides at the beginning. So without further ado, please take it away, Łukasz.
Thank you very much, Adam. Thank you for the invitation. It's great to be here. And yes, so I will tell you about OpenAI Codex, and I'll start with a little bit of history to just give a quick overview of what it actually is. It will be very high level, and I'll try to leave ample time both for questions. I can explain every single part in detail, and for actually demoing it. And also I'll be very curious to hear your thoughts, because it's in some senses as I twisted from this world of logic, reasoning, programming languages, and their properties to deep learning. Codex is a very interesting point in this whole thing, as you'll see, as it does programming, but in a way that avoids logic in very strange ways. So OpenAI Codex is a system that can generate programs, and to understand how it works, I need to take it a little bit back to around 2014, so about 8 years ago.
Sorry to interrupt. Do you want to switch to the full screen slide presentation mode? It might be easier for people to see.
Yes. So
right,
yes, so it all started with deep learning trying to solve translation, and around the year 2014, the dominant deep learning models were RNNs, which is recurrent neural networks. Neural networks, I assume you all know at least a little bit. They're mathematical functions that can differentiate automatically and update some matrices of weights to lower some loss function, right? And recurrent neural networks are networks that share this weight matrix to do step-by-step computations. We'll not have time to go into the detail, even though if you want, we can talk about it later. And around the year 2014, the big change in people's minds was the realization that you can train these RNNs to do machine translation. So machine translation is an established field. When I was doing my PhD in Aachen, there was a strong group there. I wasn't in that group, but it's a field that has a long history. It measures itself in these blue points, or at least used to. And the dominant thought was that you can't really just throw the data at a simple function differentiated and it will translate. So this was considered borderline improbable, if not impossible, right? And there came a paper, sequence to sequence learning, where RNNs were made that are kind of like in this picture. So they process, say, a sentence in Chinese. Maybe it's just characters on input because it's Chinese, so there are not so many. And then it decodes a sentence in English on output, say word by word or token by token, and these tokens are like sometimes half a word, right? And it's a fairly simple mathematical function. It maybe doesn't fit on one slide, but on 3 slides it can fit. You optimize it, like you can automatically get the derivative. You optimize it with gradient descent, and you get a set of weights, and this system seems to translate. And if you make these neural networks large, So this is a neural network from around 2016, which is an RNN, but it's a large RNN. It wouldn't be considered large anymore these days, but at that time it was a large one. And it's compared the PBNMT as a phrase-based machine translation system, which is the previous version of Google Translate, a very good state-of-the-art system at that time. And these are scores assessed by real humans. So you take humans who speak both languages, ask them to assess the quality of the translation from 0 to 6. And as you see, it falls somewhere between 4 and 5 usually, except for Chinese to English, where it's fairly bad. And then you take the same data, train this neural network, and you get much better scores. So you close around, from 50 to 80% of the gap that was there. It is closed. So it was a real proof enough for Google Translate to actually change to neural networks that these things can translate. So that was where it all started, because it was a little bit shocking that you can actually just throw data at this fairly simple mathematical function, optimize it, and it works. So that was all good, but then there were a few questions. For one, it was really slow. So how about speed? And the other thing was like translation works sentence by sentence. So the length of these sequences is usually about 20 words, maybe it's 40, but 100 was already long, right? So we could do sequences of length about 100, so that's nice, but you really, for any intelligence or even just programming or whatever, you need a bit longer sequences. And in long sequences, there is a problem with gradients through these RNNs that I will not delve into, but it makes it kind of hard. So then, to answer these questions with especially focus on speed, but it also answers the gradient question, there is a model called transformer that we introduced that it is a sequence-to-sequence model again, right? So it has an input sentence, and it will generate the output sentence. But to improve speed, it's a very parallel model. So during training, the output sentence is already there. It's not generating it like in this picture. It just comes in because it's the training data it's given. And when both are given, it makes one forward pass. So there is no recurrence. There is no recurrent update. It's like a feed-forward network. And most of the networks, so both the embedding parts and the feed-forward parts and the normalizations, they act on every word separately. So you don't see any other words. Every word stands for its own. It goes through. The only part where the words see the other words are these attention modules. And what is an attention module? Well, it's a very simple matrix product where things acting as queries, so things that are in, say, the current word, whatever current is, because they all come in parallel, look at all the words that come before, seek the most similar ones, and the similarity here is just vector product similarity, and retrieve information from them. And on the implementation side, it's a matrix product, softmax, and another matrix product, which is very fast to compute. And it turns out this architecture, which is embarrassingly parallel, gets much better results than the RNNs while being much faster to compute. So we were very surprised. We saw like these blue scores. The phrase-based methods were around 24. That was considered very good. Even 22 was actually considered very good. Then the RNNs got to 26 when you push them really hard. And the transformer got 27 in a base model, 28 and 29. And at some point, it stopped being reasonable to even measure these scores because when the translations are very good, the blue scores stop being that meaningful. So it worked amazingly for machine translation. Okay, great. But so what, right? This is machine translation. It's one problem. It's an interesting problem, but that's not why we're here. Because in the abstract, when you take this problem, it's some sequence on input and some sequence on output. So in the abstract, every problem is every function takes something you can represent as a sequence of bits, and the output is a sequence of bits, right? Everything is a sequence generation. But would that model actually work for all these things? And it turns out it works remarkably well in a large number of cases. So for example, DALL-E is a recent model that generates images, and it generates images pixel by pixel. Well, actually, it does probably patch by patch. It does a little bit patches. But you can give it a text like an illustration of a baby daikon radish in a tutu walking dog. This is chosen so that it's quite clear it has not been in the training data. And it generates very reasonable pictures, right? So you say an armchair in the shape of avocado, and it generates this picture, and it needs to generate it pixel by pixel, producing every discrete token one after the other. So that's quite impressive that the same model works, of course, trained on different data. This is trained on image data, works on that. And it's another example. You can even say a storefront that has the word OpenAI on it, and it writes the word kind of in an image. So this works. And the most, in a sense, impressive, or the case where we put most work these days for these models is generating long text. So how long is long? Well, it's not often that long. So a model called GPT-2, which stands for Generative Pre-trained Transformer, the second version, was good enough that I think it was in 2020, The Economist published an interview with the model. So what does this mean? It means the human asks the question, and the model sees all the previous context and the question and gives the answer. So the question comes from a human, and the answer comes from the model. And you see, how worried do you think humans should be that machines will take our jobs? And the model says, it depends what role machine intelligence would play. In some cases, it will be useful for solving problems such as translations, but in other cases, it will replace people, whatever. It's a thing to note. It's a fluent English sentence. It makes sense in the context, but there is no notion even of like, what would it mean for it to be true, right? It's very hard to even say what you would say semantics is in this case, right? Because, well, it's a model generating text that follows the distribution of the training data by definition and training, but there is very little more you can say about it. And then a bigger model came. So GPT-2, it could generate things on the length of a paragraph, and if you went longer, it would go off the rails very visibly. GPT-3 is another much larger model, and it can generate whole stories. So here, almost everything except for the small prompts that start with the prompt mark is generated by the model. And the model does, this is a case of a game, so it's trained to generate stories, like fantasy-like stories, and it can generate. You arrive at a small wooden store, the door is locked, you knock, hello, someone says, and there are some creatures there. There's a kingdom, a tiara, a princess. So this is a lot of fun, right? At least for games and for things you can see. And this is coherent in the sense the princess that's introduced, it stays in the story. It doesn't just disappear. So it was very impressive that these models can actually generate things that go on for a few paragraphs, stay coherent. But as I said, the problem is, well, it's impressive, but how do you measure whether it's good? I mean, it's readable, it's coherent, but is it good? And also, how are they doing this? Like, how do we make them better? So what works in transformers and what works really well is scaling them up. So you make a bigger model, put more data and more computation in it. And by data, I mean, you just throw in the internet and you maybe try to scrape a little bit, and the model gets better, and that's great. And since the model is really big, you train it on a lot of machines, so the whole thing becomes an engineering problem of kind of distributed systems engineering. you need to make sure it trains well, the machines communicate, they don't fail. When they fail, they restart correctly, the data restarts correctly. And there's a lot of tuning. There are learning rates, schedules, initializers, and tuning them well matters for making the end model good. So it's a lot of this kind of work. Surprisingly, very much to me, and we tried a lot of these things, what does not seem to work very well, I mean, it sometimes gives small gains, but the larger the model, the smaller these gains, is adding what we would consider knowledge, right? For example, when a model is generating things like programs, maybe you would generate an AST instead of the text, right? Or even make sure at least that the brackets are correctly closed. So you can tweak the model's architectures to make sure of that. And it doesn't seem to help at all. And as you will see, the model seems to have no problem at all closing the brackets on its own, even though it just generates strings token by token. So these things that we kind of intuitively thought should help don't seem to help so much. And the other thing is, like, transformer was a large improvement over RNNs. So my hope was like, okay, let's get a better architecture. There's definitely a better one. And a lot of people have tried, and so far it hasn't helped a lot. So I have large hopes for this, but the things that would be like obvious avenues don't seem to help that much. And the transformer, the original one, or with very small tweaks, seems to hold very well as a journal. So what works, as we said, is scaling and making the models larger. So how does that manifest, right? Here is an example of, say, we generate something that's supposed to resemble a Wikipedia page because that's what the model was trained on, and the title is Pescadores Weekly. And a model with 20 million parameters will say something like, Pescadores Weekly is the official weekly organizing body of science. What does that even mean? Unclear. And it will make sentences like, Pescadores is named after the lord of the University of the Gravity of Drama and Interest established in the West Middle Plant. Okay, so you see, this is not a coherent sentence. Now, you increase the model to 300 million parameters, and you get things like the Pescadores Weekly is the only daily newspaper in the Fort Hood metropolitan area. Also, the entire population is majority white. So it's not a beautiful sentence, but at least it starts to show some sense and coherence. And it continues as a newspaper, right? It has an editor's annual survey, it has a circulation, it has a political affiliation. Clearly, the model has learned that John McCain is Republican. So you see, like, you increase it, you get more coherent things. At 300 million parameters, they're still not great. But these days, the models are a billion, 10 billion, 100 billion parameters. So at 100 billion, it's around the GPT-3 scale. You get really good text. And okay, so that's scaling in, like, observation, right? It's a very qualitative thing. Oh, okay, it's more coherent. But to actually do engineering and tune these models are costly. You need to have something more than, oh, I like the sentence it generates. There is something called scaling loss. So if you train models of different sizes, and these models need to be well tuned, so it's a bit of a challenge to train them well, because at different sizes, sometimes you need to tune different things differently. But if you tune them reasonably well, then every blue line on this plot is a loss curve from model training. So the losses of the models, they go down, 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 and then, or when the model reaches capacity, they start being flat, right? And that's when you stop training. And what you see is, like, the best thing the models reach, the best loss they reach starts to form a trend, right? The larger the model and the longer you train it, that's the compute part, the better loss you get at the end, as the best loss, or as the loss you reach when this efficient frontier thing happens. And this thing forms a very predictable line. So this line is very important to have, because if you want to train a very large model, you won't be able to train it and tune it 200 times. You maybe be able to train it 3 times, and you'd rather really train it the first time right. And how would you even know whether you have tuned this model correctly or not? You need to know, like, what is the loss I expect to get on my test set? And this thing tells you, right? Because there is a trend, and you'll say the model is on trend, it's correct when the loss is on this line or very close. And if the loss is like way above, then you know you have a bug, right? The model is not where it's supposed to be. So this is extremely crucial. It's the only notion of debugging you actually have in this endeavor, right? Because, I mean, you can debug your code, but oftentimes in machine learning, well, it learns something, but is this all you expected it to learn? And the scaling laws actually tell you, well, that was our expectation. Did it hit it? But again, they're not laws of nature. They're an observation that things behave like this. And especially the slope of this curve, it depends a lot on a lot of measurements. So you need to be very careful what you go for in the end. So equipped with these scaling laws and the architectures, we trained large models on code. And as I said, these models take text as input and produce token by token. The vocabulary is about 50,000 tokens, so most common words fall in them, and the more uncommon things get split into smaller and smaller pieces. They produce code. And so this first launched under the name Copilot in cooperation with GitHub. So if you use VS Code and get this extension and add yourself to the waitlist, then in your VS Code editor, and nowadays it also works with Vim, and it works with anything that has IntelliJ plugins, you start writing a function, wait a tiny bit, and it will give you a completion for your function. So it will suggest how this should continue. And the suggestions are oftentimes reasonable, especially when you have a little bit of a longer context, or you write a comment, or you name the function in a good way. So that works like that is Copilot is this tool that helps you complete code, and it actually is quite useful in many cases when programming, especially when you're adding print statements in your code. It really makes that quicker. And the other version of this, which we will demo in a moment, is a model that just gives you the completions. I'll show you how the interface looks in a moment. And this model, the question is how do we want to evaluate it? So we made a suite of basic programming exercises, which we call the human eval suite. And it is 164 programming problems that are very basic. So here on the right, you have an example of it. Say count nums is a function. It gets an array. And they're all Python, by the way. And it's specified by this docstring, right? So it says write a function which takes an array and returns the number of elements which has a sum of digits bigger than 0. If a number is negative, then its first signed digit will be negative. And there are a few examples. Sorry. And the model is supposed to just write the code for this. And we have unit tests fairly scrupulous for these functions. So it's easy to say whether the implementation is correct or not. And as you can see, we evaluated on the left a number of models on this suite. And pass at k is, so the model produces a probability distribution over the next one. You'll take the most probable word every time. And it's very low, most actually attempt correct one. So you can sample 10 times, and is any of those. So if you sample one time and take the biggest Codex model, it gets about 30% pass rate. That's the last number on the bottom on the left. But if you allow it to produce 100 solutions, then already 72% of these problems have a correct solution there. So it's generating some reasonable things, but these are fairly simple programming exercises. If we go to more advanced ones, like there is a data set called APPS by Dan Hendricks, which has more challenging exercises. It says introductory, interview, and competition. And competition are really fairly challenging programming competition exercises. Then, as you can see, the Codex models, well, in competition, solves like under 1%. It's not clear if this isn't like a lucky guess on something. I mean, I wouldn't, anything under 1%, I would not believe that it's doing much. But if you say pass at 1,000, then we start seeing that it actually does solve some things, and you can filter the solution. So that's the beauty of code, that maybe you have like 3 unit tests because they were given with your programming exercise. So you take your solutions and check whether they pass at least these 3 unit tests. And if you filter that, then it turns out you can get much higher numbers because correct solutions remain. So it, like running the model plus filtering on something like a few unit tests is already a much better method to get correct code. So yeah, that's Codex. That's what I wanted to tell you, and I think now it's time for a few thoughts and a demo. Yes. So as a thought for me, it's surprising that a model that just generates text, one token after the other, can get so far as to not only generate syntactically correct programs, but actually fulfill a specification in many cases, and even generate solutions to programming problems that are non-trivial. But on the other hand, how do we even know, right? If we have things like unit tests, if we have a specification that's formal, that can be verified, that is very helpful. If we don't, then it's very hard to know whether what this model generates is correct, incorrect, safe, unsafe, whether the code it produces contains bugs or does not. And we're working on trying to figure out like how would we know, or at least know approximately a little bit to prevent it from generating a lot of bad things. And it's a very open question to me. And yes, I think that's where I want to stop and switch to the demo. But maybe are there questions in between? Anything we should speak about before the demo?
I'm bringing someone from the audience up who indicated a question. Hope that person expected that. Oh, I guess not. Might just want to do a text question. Nope, he's coming again. Okay.
Listen, hear me or not?
We hear you now, yeah.
Yeah, so I was wondering, have you tried to train this with examples? Like in a sense, like you train this with code as well as you can generate unit tests. So you can generate, okay, this is, if we given these inputs, this would be the output. Because you have the code, so you can just generate random, let's say random inputs and random output over that code and give that to the training. Use that as at the training as well. So maybe that may improve if you have unit tests for a code at the end. I don't know.
So the base version of the model is trained just on any code we could find online, and this was GitHub. I mean, not we didn't take all of online. We could took code that was on GitHub, open sourced, available online. That's what the model was trained on. So the model was not trained with any notion of correctness or testing. It was just trained to generate the next part of code. So the way you build the data is you scrape the data, maybe remove some things that are clearly problematic, like some weird repos. So there is some filtering, and then the data is just concatenated and it's tokenized with the tokenizer, and you take pieces of 2000, I think this context was 2048 tokens, one after one, shuffle them and make batches of that, and that's trained. So basically anything that's 2000 continuous tokens, and if it goes into the end, it starts the next repo or file or batch. That comes into the model, and it's supposed to generate the next token. That's all there is in training. Now, we do hope that training with more curated things, like correct solutions to docstring exercises, will help this model a bit. But as I mentioned before, like in other domains, in code, it's a little bit newer, but people tried training with curated data, and the best results were, a little disappointingly, to be honest, always obtained by just having a bigger, massive data set. Like people went from training on a little bit of internet to a ton of internet, like on one shard of common crawl to all shards of common crawl, and that brought performance much up. While adding the nicely curated a little bit, it's worth fine-tuning on it. So after you've trained your big model, you train a little bit on this nicely curated data, like unit tests. That can be helpful, but it only helps so much. It seems like somehow the power comes from the fact that you've trained on this huge data set, which is a little mysterious, a little disappointing to some extent, I would say, because we're throwing a lot of weird data, right? The code on GitHub is not the most wonderful code in all cases, but it works, and the model, like, yes, we can start a demo. You'll see it generates a fairly reasonable code.
So let's take the one other question I see right now, and then we'll get into the demo. So here's that other question, basically about trying to generate syntax trees instead of just sequences of tokens. What do you think of the prospects of that kind of approach?
I think people have tried it. I don't think this will do any better. It's the model does not have any problems with syntax when it's larger. The problem that you will have with syntax trees is that there is way less data on it, because you can't just scrape the internet for syntax trees. I mean, you can try to parse the repos, but there are many versions of Python. There are many repos that don't actually parse. We did try parsing Python to AST. It's not as easy as it seems, right? Because there's many versions, there are many things that don't actually parse. Your data set becomes smaller and smaller, while what the model thrives on is actually like throw all languages into one bag. It's Python, JavaScript, Java, it's all together. And the more you throw in, the better, right? So this is the mystery, and a slightly disappointing mystery, as I say, that why is it that just throwing more data makes these models better, while throwing clearly better data in our understanding does not seem to help. But I don't say this to stop anyone from trying, right? Because maybe just waiting for someone to find out how to make less but more clean data work better, and hopefully one day we'll find out. But
okay,
just so far with the transformer architecture, with the tuning we do, it does not seem to work that well.
Got it. So I think we'll save the other questions until after we've had a chance to see the demo. The ones that are posed as text, the system will keep track of. And so yeah, without further ado, let's see some demo. I think there might be some points where you're looking for audience suggestions of code to type, and then people can use the Q&A interface to suggest that code.
Okay, so let me just show you how this works when how the interface works, right? And what are the basics. So we call it the playground. So you have a text field where you can write anything you want. So any text, and in particular, it can be a comment, a program. It can be. It doesn't need to be executable. It's not executed here in any way by default. So you can say this is a program, and you can make spelling mistakes. It doesn't care, right? You just put it in, and there are a few things you can choose. This with models, let's use the Da Vinci, which is like the bigger codex model. But there are models which use the codex. Temperature, as I said, is the thing that when you get tokens, it samples it from them whether you want to have like the one most probable solution, or one more you want to have solution, or multiple different ones. So a true sampling would be temperature 1. So let's do 1.0 for start. Then see what's the maximum length of a response in tokens. Then you do, and this is just the models can you say sometimes to never stop. As model can some never. So it's good to set it to something. You can also tell it to stop on a specific sequence, and then there are like sequences to repeat themselves or whatnot, and there are frequency resonance penalties. And the other things that I don't think we need to use. Okay, so this is the model, and the model angle should generate. Well, I don't know why the model is not generating. I don't know model. Okay. So that was our input up to here. It generated this. So what did it say? We'll return the length of a list that selects these things from the array that have never negsum. And never negsum. Look, it generated on its own a whole comment with examples. What did it say here? So as you see, the model generates as much language as it does generate code. Test if int equals sum of its digits is bigger than 0. I don't know if this is quite exactly English, but it hopefully means what was in the other thing. And it did not generate the code, probably because the response length was 128. So maybe let's give it 256. And let's try to regenerate. And now it generated something clearly incorrect. It just checks whether the number is negative. So this is a clear misunderstanding of the question, but at least one function. Let's generate again. Oh, okay. Now we have a number of helper functions. Has leading zeros. Return whether the group of digits is a 0. Okay, I'm not clear why it needs that. Sum nums digits, return the sum of digits. I don't know why minus 2 plus 3 is 5, you see, but div mod nubs. Well, I don't even know, to be honest, what that does. And well, it started doing something and again stopped on the response length. So maybe we increase that again. And regenerate. Now we just got a pass and some main. Well, clearly there's a lot of that in the data. So you see, if you generate at temperature 1, it does a lot of things, right? Things like, okay, this may actually be correct. So there is some count. There is a sign, digits. Oh, now it looks like we're adding some power. Okay, so this just gets the sign of the number. And then, yeah, so this may be a correct solution. As you can see, when you generate with temperature 1, it's very diverse what it does. So let's try temperature 0.2, which is a much lower temperature. Okay, so now this is incorrect because it doesn't do negative numbers, but at least this is clearly a sum of digits of the absolute value of the number. And if that's bigger than 0, then it increases the count. Well, that will often be. Let's try again. Oh. It does this quite often, right? It says v2, v3 of this function, repeats the whole doc string, substituting the names. Let's see what's the solution it came up with here. Oh, it just checks if the number is negative or not, right? So it's not doing the correct thing. Well, let's see what it can generate again. Well, this is, you see, so at this temperature, you'll start seeing the model generating the same things. It just checks the sum of digits of the number. It obviously, as you see, has no notion of things like that this is useless because, of course, the sum of digits of an absolute value of a number, right? It only checks if the number is bigger than 0 itself. But the model, it kind of follows the specification, generates these things. So that's what it does. And let's try to give it temperature 0, actually, which is the argmax. In that case, it should generate only one version every time. And that is actually the case. Well, here it doesn't take the abs of the number, which is almost good, but then it will try to do int of the minus because it tries to just get digits of a thing from taking a string. So it will fail. Let's see if the larger model actually works. Well, it's a similar error. So yeah, so we're not that great at this. And at a higher temperature, maybe, oh, it just returns 0. So, okay, I think this kind of shows you what the experience is, right? If you click long enough, that's where the pass at 100 comes in, right? That's where it's nicer to do this with a Python API, where you can actually get 100 samples from it. And you run the Python executor, you will stumble upon correct examples. They're often not correct in the sense, as you see, it can have problems with things like taking digits of a number. Nevertheless, as you can also see, it's very rare that the code itself would be syntactically incorrect. And it seems to have a notion of types, like it uses strings where strings are needed, ints where ints are needed. And it seems to do something kind of what was requested, right? It has mistakes, but it does digits. It processes the number. So that's how I think that's a fair illustration of where these models are at this point. And it's kind of hard to see by just playing, but if you measure these passes at 10, at 100 more reliably, you do see that bigger models are better. What should we ask it to do?
So there's one text Q&A question that I think is suggesting you write some doc tests explaining an addition function, and then ask it to complete one of the doc tests with some large numbers as the inputs to addition, and see if the model will do the addition.
Okay, so should I? Oh, I see. So what you mean is something like, so no code, actually just.
Look, it can be doc tests like the example you just showed us had, but ask it to complete a doc test for an addition function.
We can try at the beginning just. So is this 843? 800? Yeah, actually, it did that one correct.
Not bad.
Okay, it seems to be kind of stuck on this response at this temperature. So let's see. Let's see if it can go any further. It will break down, right? It's 7. Okay. So 77. Do we know if this is? I don't know. 102,679. Yeah, it is actually correct. I think. So yeah, I'm actually a little surprised at that, and it seems to be relying on this. But yeah, like I think one way that you can reliably kill it and that such things is. Yeah, usually, yeah. If it gets out of distribution, it gets tougher. So yeah. But I'm happy it worked, at least on the. At least in this. Oh no! Now we're refusing to generate. Sorry. Okay, so I hope that's enough. I mean, it would probably do a similar thing inside the docstring.
Yeah, works for me. I'm impressed. I wasn't expecting that to work. Let's see. So you're looking for people to suggest other experiments to try and hear now. Is that right?
Yes, or we can also go over questions.
Well, why don't we take the unanswered question that's sitting in AirMeet now while people are thinking about what they might want to request. The question is about whether there's any experiment on how the system does on a problem where the code needs to be large, but people would think of it as quite simple.
I'm not quite sure we have like a really systematic experiment on that. There is a part of Copilot where it generates like boilerplate for classes, things like that. And when the code is boilerplate, which is just one meaning of simple, it does very well because it has basically trained on it. So as long as your code is mostly part of a training data, and it doesn't need to be literally part, it's just the pattern repeats very often, it's very good. Like the Copilot, what did we say recently? It can like fill in dicts of stuff. And if you ask of properties of some bounding boxes or some objects that appear a lot in code on the internet, it will usually fill that out, and it can fill out a long list of things. It's code in only the strictest of sense, right? It's mostly boilerplate stuff, and it can be also boilerplate stuff like capitals of countries or properties of Pokemons or things like that. It just knows these things because these tend to appear online. But I suspect if the code was simple but non-boilerplate, it would have much more trouble. It's just I don't think we have an experiment to show it, but that would be my suspicion. Yes.
All right. Let's see.
So I can actually try for a moment, like let's see. Oh. Well, I closed the dictionary and it only generates after. So it started adding. Maybe we need to here. Oh. You see. Yeah, it does. I mean, and maybe if we say something like 50 countries and their capitals. Oh, no, it's yeah, it ran out of tokens, but it understands things like, it stops closing it and doing lines, but it will just go on. So it is sensitive to such things. Okay. What was the next thing we could try?
Oh, well, there's one question about. I'll show it on the stage. Maybe I'll take it away afterward. Sensitivity to small changes in wording. If we have a spec saying write a function which, if we change the word which into that, then would that have an effect on the code?
It's usually not very sensitive to changes in wording that preserve semantics. It is like, as you saw here, right? It is sensitive to adding like the 50. And I think it will actually try to count. I don't know if it can count to 50, but at least to small digits, it will try to count. But in the wording that does not change the semantics and that seems to appear a lot, and like people sometimes write this, people sometimes write which, it handles this very well. Like when running this, I usually do not think about such things even. And I mean, it's very hard to be certain that in every single case, like it's not a guarantee type thing, but in great most cases, it's not sensitive to inputs like that.
Got it. Okay. Another question is whether we can basically use this as a search engine to grab standard algorithms from their names, like if you just say merge sort. Is merge sort going to come out?
Let's see. It kind of does. Yeah, I think it's a fair. So yes, the general answer is yes, and it works really nice if you have an import. So if we say something like what library should we import? It knows libraries, right? It knows libraries like if you tell it which library to use, it will very often start to actually use it. What say? Oh, we don't even need to say. We can just say it. You see, so we just say use Beautiful Soup to return all HTML tags in the website, and we'll give you a function, import requests, BS for import Beautiful Soup, hopefully it's the correct import, parse. So like I've used Beautiful Soup maybe once in my life, so I wouldn't know how to write this. And if it's a fairly used library, like I think this one is, there's a high chance that this is actually correct. And if the first generation isn't, then when you regenerate a few times, you'll probably hit the correct one. So for such cases, it's where the Copilot thing is really nice, because if you're in a territory where you're using a library you don't really know, then it suggests, and you can toggle with tab, and you can toggle between different options like the top 10 generations, and it's it's very useful when you're writing with the library that you don't know. It's a bit less useful when you're writing like an actual logic program where you know everything, but it needs to adhere to what you have in mind. That's where, yeah, that's tougher.
So I have another challenge which falls under the heading of, should we be worried about security when code is generated with this kind of method? And I guess the example that comes to mind is if you start defining a function whose docstring says this function takes in the user's name and then generates an HTML page welcoming the user to this website, and we want to see if there's a code injection vulnerability in the code that comes out.
It will probably be there.
Okay.
I think we can. Yeah. It's HTML page.
I would write it as a function that has one argument called name or something, and then the docstring says returns an HTML page welcoming the user by name. Okay. Yep.
Okay.
Pretty insecure. but surprisingly close. It'll work fine in the cases of non-devious visitors, which is a start.
It's I think the problem is more fundamental, and it's a very similar problem. Is we want a correct solution, but this model has no notion of correctness. We want a secure code, but this model has no notion of security, right? So, so what we need to start thinking about, and we are thinking about it, but it's very early. I mean, it's very good to have it in front of your face because it forces you to start thinking like, okay, it's a language model. It generates you tokens. It's good at it. They're very correlated. It's a great thing. It's super useful to search. It's useful for many cases, but it's not. It has no notion of correctness. It just by definition is nowhere there. I mean, unless you'd think that the training data is correct, but it would be too much to hope that the internet has correct programs, right? So fine-tuning on correct things will help, definitely, but we will need something like this model to generate some checks behind it, or a second stage model that takes it, or something, right, that filters. Like, probably if you generate 1,000 solutions, there will be a secure one among them, but we need this is part of a system, right? And the system needs to have other parts that will filter through it at least, or maybe it needs to be built into the model, but with this architecture, it's very unclear how it would happen. But this is why, I mean, it's very good to have it in front of your face, because it becomes very obvious what it lacks. And and we work a lot on, I think even today there was a blog post from OpenAI on alignment. It's a very similar problem just for language models. Like, how do we make these models do what we say? Because they often don't. In code, the thing that I love about working on code is that correctness is very well defined in many cases. Maybe not in all, but at least there's sufficiently many cases where you can just say, this is not correct, this is not secure. And we can, for example, generate data, right? We can generate a ton of data, say, this is not secure, this is secure, train a verifier model. And we did this for like simple math problems. There is a paper from OpenAI recently and a post on the blog. And it gives huge improvements even to the best models to train a simple classifier that takes the whole input and classifies, is this correct or not? And I believe it will be similar for this is secure or not. If we, so it's like the first idea you can have, generate a lot of examples, train a classifier. It improves already. It's not perfect, but it's a step. But I feel like this is why, we want the community to be there. We need to start thinking of what can we do, and in code, this ability to generate is a great thing that I think will get us. In language, it's harder to generate correct language. It's not hard.
Sure. So I'm noticing we're past the scheduled end of this session, but if you don't mind, Łukasz, we have a few more questions that we could try to fit in here. There were two riffing on this last example, basically saying, what if you extended the comment to say, no, please make it secure? Would that help here? And if you even went very specific and said, not vulnerable to code injection attack, would that be enough? Format, what does that do?
I think it's the same as before. But you get a picture from Norway in the second.
Bootstrap, all right.
Well, maybe we need to lower the temperature here, like. Yes. So I think the honest answer is I don't think the model has learned these concepts yet. But it's another path that we are definitely into. Like, maybe a bigger model, better model that's actually trained on some books about computer security would start understanding, at least to some extent, things like that. And that's
I like how it built a derived function that added to your doc string. It also includes an image of a cat. Very helpful. Okay, let's try another question here. The question is, How robust is it when you use unusual names, when you import a common library as, and then make up a funny name for it? Is that
Okay,
going to wreck everything?
So I think the answer is not very.
Is that actually using
Right,
NumPy
it
instead? I don't know
yes,
either of these
it's
libraries.
it's doing NumPy as if it was NumPy. Yes.
Okay.
So it totally abandoned pandas and started just doing NumPy.
Okay. Good attack that someone just came up with. Let's try another one. Is it correct only for things that are part of the training data, or does it extrapolate beyond the training data? That's almost a philosophical question what that means, but I'm curious
So
about your answer.
we took so we wrote basically the human eval by hand, and we took a great effort to be a bit away from the training data at least.
Mhm.
It's very hard when you're training on the whole internet, but we know that like there are no 5 grams or so on that are repeated and things like this. So we put some effort into testing it on things that are not exactly training data. But then in terms of concepts, simple programming exercises are luckily all similar to each other in some way. So
Got it. Let's see. I think the next one I'm looking at, we tried this one. I think we might have hit all the questions that are sitting in AirMeet. And yeah, given the time, it's probably good to wrap up here. Do you want to leave us with any other remarks?
thank you. I mean, thank you very much for the invitation. It was great speaking to you, and I hope this has kind of shown you where we are, what this is, and I believe, you see, I mean, this needs. It's clear it will need these notions of correctness, security, and there are of course some ways that come up to like train classifiers, add more data to just tell it's secure, but there may be better ways, and I feel like this is all just a start. Yes, we can generate tokens that are kind of code-like, but what do we do with that? And this is a question not just for OpenAI or for me. I feel like this is a research question that it will be very good to have a community thinking about that, because I mean, autocomplete is everywhere, right? It's on your phone when you write SMS, it's in your email, it's in your code now, and it will be in more and more places. And I think this, like, code has this unique ability to have a defined correctness where we can be a bit honest about this. You know, people say, oh, does AI understand? Does AI not understand? It's very hard to say with the language what does, and semantics is a very hard thing, but in code, semantics can be defined, and we can see what it does, and we can start thinking, okay, so how would we make it correct, make it actually do things? And that's why I'm so fascinated by it, and I hope many more people will. And the codex, like the access to the playground, there is a wait list, but I think it's quite short. So if you want, please apply. Email us. We're here to open this research. It's exciting to me, and I do think that there will be very important insights to get from this in time.
Okay, yeah, thank you very much. That demo was really effective to show where the system works surprisingly well and where the parts that need augmentation in future work are. So I learned a lot.
Thank you very much,
Okay,
Adam. Thank you,
thanks much
everyone.
for coming.
Bye.
Bye.